Hello everyone. Welcome to my seminar. I'm very pleased to be able to talk to you about the issues regarding the slope course. The slope course is a course I have been giving for a number of years. I'd like to introduce myself first. I'm a geotechnical engineer uh, with slightly more than 50 years in geotechnical engineering. I have worked on many projects, many interesting projects, all types of geotechnical structures like slopes, dams, foundations, etc. I'm still working hard on a few international projects, and I most of my career was in Brazil. Now I'm recently we have been changing. I have been changing to do international projects as well. I have a few projects in the US, and I spend time in the US, I spend time in Brazil, as I have family in both countries. And today we are going to talk about anchors, bolts and nails, initial part of the presentation. Then we're going to jump into tieback walls and in the end, soil nailing. I hope that we are going to talk about a couple of hours about this, and you're welcome to present questions and discussion at the end of, so we divide the lecture into three parts. At the end of each part, you are welcome to come up with questions for our discussion. And so let's get started. The contents of the lecture today has the following contents. Tieback walls. I'm going to talk about the first tieback wall I've ever heard about. It was built in 1957. Certainly, it's the pioneer work. We're going to talk in the next part. We're going to talk about concrete reinforcement steel bars. The use when we started, we didn't have the threaded bar, so we used concrete reinforcement bars. Then threaded bars came up. Today is the choice. And I'm going to talk a little bit about multi-strand anchors, corrosion, which may be a problem, and we have to address this carefully, and grouting, and testing, how we do testing. And by doing testing, we come up with rules to get friction, soil anchor friction, okay? Soil nail friction. And so there are what we're going to discuss today is tieback walls and soil nailing. What's the difference between tieback walls and soil nail wall? The tieback walls is an active reinforcement in which all the tiebacks or the ground anchors, they are pre-stressed to a particular value working load. And on the other hand, the soil nailing technique, we use passive reinforcement in which the nails, which are very similar to the tiebacks or the ground anchors, the nails are not pre-stressed. And how do they develop, how they mobilize friction? They mobilize friction when the wedge, the failing wedge, tends to move. If there is a displacement, a very small displacement, this is going to imply in the nail to work, to develop friction, and that's the way they work. Basically, we are talking about the difference between an active reinforcement with pre-stressed anchors and a passive reinforcement with no, in the beginning, they are not pre-stressed, okay? So this is the difference that we're going to talk during the class. Anyway, since the first tieback wall I've heard about in soils, it happened in 1957. I'm going to address this later on. And this type of tiebacks have been used a lot, more or less until 1965, or perhaps about that time, when the threaded bar started. So these most of these tiebacks in this time, they were 25 millimeters in diameter. The steel grade in the beginning was what we call C825. Later, the shear strength was very low, about 250 megapascals, and the testing load was about 1,000 kilonewton, and the working load is about half of this value, so it was about 500 kilonewton. That was more or less what was used. And in the beginning, as I'm going to show you, there was no corrosion protection. People were not very concerned about corrosion, and a lot of problems, of course, did occur, and we are going to address that. And at some stage, I think more or less in the 70s, perhaps a little earlier, the market had much better bars, which are threaded bars, and they are very easy to splice with a connector like this. So the other one was very difficult to do that if we have to increase the length beyond, in most cases, 12 meters. If we want to increase the length, it was a big problem because you have to weld, and welding this kind of bars may not be very easy. And also, very easy to put the plate and the nut to transfer the load to a wall. And so this was a big advancement when this came up. I think in late 60s, early 70s. I don't remember the exact date. The other thing that I'm going to talk about is that grouting. And to do grouting, in most cases, post-grouting, we need what they call manchette valve. This was developed for the first anchors that were used. And as you see here, these anchors are being prepared to be used for post-grouting. And this is the steel bar. And here's the grouting tube. And here's what we call the manchette valve. What's the manchette valve? Very simple. We have a tube, a plastic tube like that, PVC, and then there's we put some holes in, and this is the cover, which is a rubber hose that we use to do. And when we put pressure here, what happens that this rubber hose or the manchette valve is going to open due to the pressure, and the grout will be able to flow outside. So these are the techniques that are used. This photograph is about 1990. So at this time, corrosion protection was a major issue for long-term application of ground anchors. And what we see here is a free length, the grouting tub, the resin-coated bonded length, and centralizers. I'm going to describe all these details. These for ground anchors, in which we have a grouted length and a free length. So let's have a look about these details. One of the important details is spacer, to make sure that the steel bar is going to be sent in the correct position, centralized in the borehole. Okay, this could be done by very simply by made from PVC pipes. I'm going to show you is something that in the past I used to do at a construction site, or it can be a little bit more sophisticated with a special piece of plastic that we put around the bar. This is the very simple one, which we can manufacture on site, and this is the protection here is a resin-coated bonded length. Today, this is not very much used. I'll show you what kind of protection that we use. We tend to use more today. This is typical centralized, homemade centralizer, but it works nicely. And The other thing that people didn't in the beginning, they didn't account for was corrosion. Okay, and then it turned to be a major issue with time. The corrosion rates can vary a lot from countryside, urban area, industrial area. So, and also if you have any kind of contamination in the soil, if you do that, you may have high rates of corrosion. Also, when we are on the seaside, very close to the seaside, you have to address this carefully, like this tieback wall. This was very close to the seaside. It's about 30 meters, 40 meters maximum from the shore. And of course, there might be some salt sprinkler. And then corrosion rates in this case was very important. And this led to, for instance, if you the corrosion rate is going to make the steel to expand a little bit, and then the protection fell off, as you see here. And this has been repaired already some 10 years ago. This picture is from about 15 years ago, and about 10 years ago it was repaired. So as we see here the rebar being exposed, and this is very bad, of course, and you have to do maintenance. I used in the past multi-strand anchors, and we were very cautious about that because in such multi-strand anchors may have a very high rate of corrosion. And why? Because they are very small diameter, usually 6 millimeters. And corrosion usually takes place with 2-3 millimeters. So in a case of a big bar, you can allow for corrosion, reducing the effective diameter. In this case, you can't. So these have been used technically. It looks like very good because you can have multi-strand anchors, and then you can have a very high capacity ground anchor. But until recently, I'm going to show you a solution. Until recently, it was very, very dangerous, to the point that I have seen corrosion like that, in which all the strands have been reached failure due to corrosion. This is another example, tender corrosion. You see what can happen. And also, corrosion is in these multi-strand anchors can be faster because you have a tendency of having, you have a small misalignment of the load. Then you have a flexure close to the head. You know, I remember a friend of mine once gave a lecture on this kind of uh, bad bad practice of not protecting these multi-strand anchors for corrosion. And as a matter of fact, I've seen a few failures due to this bad application of multi-strand anchors without a proper corrosion protection. So, corrosion protection levels. Most standards they have at least 2 or 3. Single epoxy coating and grout. I'm going to show you some examples. And double when you have epoxy coating, corrugated plastic sheath, and grout. This much better. And how does it work? If you see here, this the steel bar, then you have grout in here in the corrugated plastic, and then there's this plastic sheath like this one, which protects entirely the bar against the ingress of water, and then you may have a very good corrosion protection. This is an example of, as you see here, the steel bar, grout, and the plastic sheath. Multi-strand anchors, these are good corrosion protection. It's a job that I have done in the past. And here we used these multi-strand anchors, but they were all protected by a plastic tube. So this is much better. And also, some countries allow epoxy coating and consider this as a single corrosion protection, which may work, especially if you have a large diameter bar. This could be used as well. It's very interesting. I'm going to address my experience in Hong Kong. I worked there many years ago for 6 months, and I visited some sites and also visited the factory they used to make these ground anchors. And the corrosion protection was made of galvanized, using galvanized bars. Okay, they had a factory to provide the galvanization to these bars, and they measured these instrument is to measure the thickness of the protection, and that's what they use in Hong Kong, and seems to be very successful. An example of a nail used in Hong Kong, in which they used, of course, they must use a centralizer. This is the galvanized bar, and here the grouting tube that runs alongside the galvanized bar. And this is another example of corrosion protection by resin coated bars. And here's the centralizer, and here's the grouting pipe running close to the bar. This Dividag anchors was a project I have done in Argentina many years ago, and very, very good corrosion protection. Also, they have grouting pipes, 3 or 4 grouting pipes per anchor to allow, as I'm going to show you later on, we can do grouting in stages, and this could be very effective. Here's the centralizer, and the free length, we substitute the grouting by grease, as I'm going to show you in these anchors. Loads. Usually you consider the testing load of 90% of the yield load of the steel, okay? So more usually for round anchors, we test all of them to this value, and then we reduce the load by dividing it by this test load by 1.75 or 2, it varies according to standards. And here, recent developed by Dividag permanent ground anchors. It's a very good solution, and it's a threaded bar, fully protected, and they have diameters from, say, 32 millimeters to 75 millimeters, and working loads from 350 kilonewtons up to 1100 kilonewtons. And here you have the centralizer, how it is protected, the anchor head with the bolt, with the plate to transmit the load, end cap here. This is a temporary ground anchor. What's the difference? It doesn't have the same corrosion protection. Here you have no corrosion protection here at the where the bonded length, at the bonded length, which is here. This is the free length, this is the bonded length, and no corrosion protection. How do you use these temporary ground anchors? Usually for excavation, in which I have used a lot of temporary ground anchors for excavation, in which later on we're going to have a slab receiving the load of the wall. So these temporary ground anchors only work during construction. And this is the solution of permanent multi-strand anchors, which has been developed by Dividag. Every strand is completely protected, no way of water ingress here. So this type of multi-strand anchors could be used for permanent application, and they have, as you see here, working loads up to 1,000 kilonewtons. So from very low with one strand up to 8 strands, going up to 1,000 kilonewtons. And here is temporary multi-strand anchors with no corrosion protection. Okay, I have used this a lot for excavations, usually for loads 1,000 kilonewtons. That is difficult to use the bars. It's more expensive. This is cheaper and very effective. So for temporary application, I have used this a lot. And soil nails. Here you have full corrosion protection, also and for temporary application, just epoxy or galvanized. In some countries like Hong Kong, south of China, they use this a lot, just galvanizing, and they are very happy with that. And as far as I understand, there's no big issue of corrosion where they have been using that as a soil nail. Okay. Cement grout. The cement grout has some properties that we have to follow to maintain the quality. One of them is to have a water cement ratio less than 0.5. Use of admixtures that to allow the grout to swell, and setting accelerator if necessary. High turbulence mixers, if this is the case, okay, this is the case, the mixers. And usually what we require from the ground is to have a 7-day strength and confined strength larger than 25 megapascal. This is the most important attribute, okay? And also degrees, we have to use degrees for the unbonded length, the free length, okay? What's degrees for? To avoid contact with water and water ingress, self-healing, thixiotropic, and microbiology active resistance. And I've searched the market in the past, and this was one of the degrees that we could use from Shell's Ferroprot 4450. There might be many others in the market. So, but at that time, I did the search. This was seems to be a very good one. And degrees then is used in the free length, as you see here. Okay, the bonded length, you have grout under this sheath corrugated pipe, and here under the plastic pipe we have degrees as it comes out here. I'd like to point out two main points for corrosion, which I've seen many times. When you have jointed rock, so water can flow here, and it's going to affect very much this part of the boat or the anchor, and corrosion protection has to be taken care of. Also, this part here, if you have a kind of a big boulder fixed by rock bolts, then corrosion protection should be applied because the possibility of having corrosion, accelerated corrosion at these points is very, very high. Then final stages for the corrosion protection, especially in tieback walls, to repaint the steel parts, which the steel parts are need to repaint, the boat, the heads, etc., as I'm going to show you, and to do a head protection, as I'm going to show you, and post-grouting of heads. Okay, this post-grout is very easy. And how we do that? This is the head of a tieback wall. And what can be done easily is to leave these two grouting pipes. So this is the protection cap. All you have to do, repaint the bolt and the distribution plate, the steel plate, and then we put this protection cap, usually concrete, and then we use this grouting tube to grout just by gravity this region, because this region is where most of the problems take place in most cases I have seen. Okay. Another very good solution for to avoid entirely corrosion protection, but the cost is a little bit higher, is fiber reinforced plastic nails or anchors. Okay, this has been in the market for some time. The advantages are high and adjustable tensile strength, high and adjustable Young's modulus, high dynamic strength, excellent corrosion resistance, no problem with corrosion usually, low unit weight, very light bars, and magnetic electric neutrality, so we don't have any magnetic effect. Okay, easy to cut. Properties of this fiber reinforced plastic. This is common construction steel. Okay, it has a strength of about 500 megapascal or 0.5 gigapascal, and this is press-acid wire, which is about over twice. Okay, and here's some of these fiber reinforced plastic: carbon, glass, aramid, and as you see, it has a very high tensile strength, but there are some catches. And the problem is the tensile strength is very high. The model is very low. The weight is very low, which is good for applications. And here are some examples. For instance, Dividag, this international company that makes this steel bars, etc. They also do FRP. They have solid bars, hollow bars with a drill bit. And the problem is, here's the diameter of these bars. This is the tensile failure load. The problem is it has a very low strength against shear. Okay, this is the problem. So the head has to be manufactured in a way to be for this maximum load to be applied. And maximum head load, as you see here, although the tensile failure load is very high, the maximum head load is very low. So this is a problem. Okay, in all and why? Because they have a very low shear strength. And here another manufacturer from Canada. This, of course, is available in America as well. And here you have they have a different solution, which they put a threaded envelope here with a threaded tube, and this plastic FRP goes in the middle. So, but the same, we have a very low. It's not easy to go to the ultimate strength, tensile strength of the plastic bar. Okay, but these are very, sometimes it could be a very good solution where you have contaminated soil. And I'll show you an application. It's not related to slopes, but in which these bars can be used very effectively. This is an example in Britain of a wall in which everything has been used, everything was made of plastic, except, of course, these profiles here, which distribute the load. So we have a geogrid, and we have these FRP bolts, okay? This was a very contaminated site. That's why they used this solution for a wall. And this is not related to slopes, but this is a very good solution where we must use these FRP bars, is nailing the tunnel face, okay? When you do that by nailing, it's very easy to excavate. If you have done it with steel bars, it would be a big problem. Okay, I have used this in a few tunneling projects, and it was very successful. And uh, let's talk a little bit about friction on anchors and nails, and how can we get this information in order to design the bonded length of a nail or ground anchor. Here's the typical setup to test for friction. You have here's a jack, hydraulic jack. You have a load cell here, and then you measure displacement as well. And here usually you have 1 meter free length, and then bonded length of 2 to 3 meters. You can't be longer than that, because otherwise you're going to have a failure of the steel. And what you want to do is a pull-out test, in which you extract the nail of the anchor in order to obtain the value for friction. Okay, and this is a typical setup. Okay, with the jack, with the load cell, you're doing a test, and another one, the same, jack, load cell, etc., etc. And the first time I came across a lot of data to design this kind of friction was some publications from Bustamante Douat in French. They were engineers of the Laboratoire Central de Pont-Chaussée in Paris, à Paris. And the problem with this, and they have done lots of tests with soil nails in sands, also in clays, as I'm going to show next. But the problem is, here you have the SPT value. And SPT in the beginning here is 0 to 10 to 20. So here, SPT of 20 is a hard soil. And still, we have a very large scatter. So if you have a soil with 5, what kind of friction can you use? It's impossible to extract this information from this type of graph, type of plot. They also have done it for clay and silt, and the same. We have here a very large scatter, and very difficult to extract unless you have a very hard soil, let's say of 20, any SPT of 20. Unless you have this, the scatter is too large to allow this for the design. And this affected me a lot, because I was involved as a consultant to the Brazilian underground. It's underground system in Brasília, the capital of Brazil, and between 93 and 94. And I didn't have any information useful that for me to design. And then what kind of soil do we have there? It's we call it a porous clay with a very low SPT value, like 3 to 2, 3, 5 maximum. And we didn't have any data. So I started a program to test nails in order to make, to prepare plots that would allow us to come up with design. And I did also vary the borehole diameter. As you see here, very interesting, this porous clay. Although we varied the borehole diameter, the friction was more or less constant, about 8 kPa of 70 kPa. And in this this site in Brazil, it's really formed of porous clay and slate saprolites, and we did a lot of tests in those materials. And most of the case, in porous clay we had a value of 50 kPa. Friction was not more than that, and slate saprolite, there was a large scatter in which we had, from 100 to 200 kPa. So and then I started not only Brazil, I've been in many other projects I've been involved in my life. I started plotting these results, and later in 1997, Palmeira, a professor uh, of geotechnical engineer at University of Brazil, and myself, we published the results and we published these limits, these correlations for use. And this, I have used this in many projects, and this, in most cases, work very well as a prediction. Okay, but we always have to test at the construction site at least 1% of the nails to make sure they work. The other correlation which I came across, not a correlation, a prescription, is friction in rocks, in which that's what I use. Usually, if I have hard rocks, which most of my time I have dealt with hard rocks, I use a maximum of 800 kPa of friction, soil nail friction, and these also work hard. The other thing that we learned in practice, and there's a trend to do that, is we have a much better behavior if we do phase grouting. And how to do that? And this is a nail, and we have three injection tubes, one to the tip, then the middle, then the last part. And by doing this kind of injection in three stages, in most cases, we have a much better result rather than just one stage that was the practice in the beginning. The other thing that we are doing, I'm going to talk about a little bit about that. When you have inclined slope, let's say 60 degrees or less, in most cases, we don't need the plate, and we just bend the steel bar like this, and it works. So we're going to discuss this later. So here's a kind of correlation with multiple phase grouting, the relationship between no just one phase and multiple phase grouting. Usually we have an increase of, say, at least 50%, at least 50% with this technique. And this we have a lot of data, field data that show us that multi-phase grouting is a very good solution. Doesn't cost that much and is very good. Okay, so this is the end of the first part, and if you have any question and discussion, you can either write on the chat, or if you can send me an email, or use the WhatsApp, and I will answer uh, any question. Yeah, I'll try it at least. Okay, so let's go to we stop this part. Let's see what I do. Okay, now I'm going to the second part of the seminar. Let me start over here. Just a second. Okay, Now we're going to talk about tieback walls, okay? And as I said before, a tieback wall is a wall, well, of course, with tiebacks, but they are pre-stressed to a high load. Usually we test up to 90% of the steel strength, and then we reduce the load to half of that testing load, and that's the way it works. Okay, and I'd like to talk about the first tieback wall I ever heard. This man here was Professor Costanuni. He was my professor at school, at School of Engineering. I was his student in 1971. This was my last year of the engineering school in Rio. And he was also in addition to being a professor, he was also the owner of a very large geotechnical engineering company, design company, and he used to do also specialized works like uh, ground anchors and things like that. And he told us many times in class a few things about this first trial. He did it in 1957. I was very young. I was 9 years old at this time. And this is a hotel, a big, sorry, a hospital. This is the hospital called Beneficência Portuguesa. It's a very old hospital founded, I think, in 1840, in the 19th century. And they want to build this new one. So in between the old building and the new building, they want to put this hospital on a different level. So there was a need for this wall. And he told us that he designed this wall for the first time. He also pre-stressed the anchors. Then the working load was half of the testing load. And but he never published anything about that and details. He told us many times, but we didn't know where it was. And then in 2 years ago, uh, I decided to find where this first tieback was. And I searched with lots of friends. I have worked with Professor Costanini for at least one year in his company. And I searched with my colleagues, my former colleagues, and then none of them knew. And we went there and we took a lot of photographs. So it took us the people at the hostel, they were very concerned about allowing us to check the wall, but in the end they did. And what we found is that the wall wasn't continuous; it was like a grid. And Professor Costanuni told me that in the beginning he designed like this, and then but it was the only one. Later on, he found out it was much better to have a continuous wall, and that was he did in the end. And the wall, the lady that received us, this my friend that knew where it was, and so this seems to be unless new evidence comes up, this seems to be the first tieback wall in the world. Because he used to tell us, Professor Nunes used to tell us that the Germans were the second to use this kind of technology, but they used 1 year after this experience. And the wall, of course, presents signs of corrosion, as I've told you. In those days, they didn't make any corrosion protection. And these were usual concrete bars, concrete reinforcement bars, 25 millimeter in diameter. And everything was new here in 1957. I'm very proud that I have found this old work from my professor. He was a man that developed lots of things in geotechnical engineering. He was a pioneer in several things. And I had the privilege to be his student. So the Brazilian experience, we had the first tieback wall in Rio. He published, Professor Nunes and Veloso, they published a paper in 1963 about the analysis, what kind of analysis they have done. And later on, in 1967, after very severe rainfall and lots of casualties that took place in Rio, Rio founded the Geo Rio, which is an organization, a city hall organization to look after slopes and to reduce risk. And I have talked about this in other classes. And 1984 was also a milestone because we have this 35 high wall, perhaps one of the first so high with soil nailing. It was a mix. We saw nailing and ground anchor as well. I'm going to show you that. The construction stages for this was developed by Professor Nunes. Construction stages for tieback walls. In many cases, we have to do it in niches, as perhaps you see here. Why this niche? To keep this niche prevent the wall from falling and also increase the maintain the factor of safety of the slope high. If you don't do that, as I'm going to show you later, we may have accidents, as I've seen one of them. So these niches are very, very important. And these, until this time, until 1957, all the walls, we have to excavate a lot, we have to put a masonry wall or gravity wall. And these walls were taken from the top. We constructed from the top down. So this was a major change in the technique. As you see here, the niches, excavation phases, and here also this slightly different wall with precast elements, okay, that was used as well. And also they have multi-strand anchors, which in those days, this was very dangerous because of corrosion. Today, it looks like that we have a good solution, but in those days, we didn't, as it's shown here. So, failure types that we have to analyze for tieback walls. Base punching, for instance, toe failure, okay? I've seen this to occur many times. This toe failure, I'm going to show you during construction, but I haven't seen anything like that. No, there's one example. I have seen one example, toe failure. Yes. Also generalized failure that may take place. I've seen one of those as well. Wall failure, I've never seen, okay? This is a case of generalized failure, a slope, and this, it's a railway in Brazil, and this took place, major failure. And as a matter of fact, is a video showing what happened, okay? The probable cause of this was corrosion in the anchors, okay? I have seen many cases like that. Anchor failure, I've seen lots. Okay, in this case, it's a major motorway. This is BR 040 that goes from east to west. And this was a major failure that took place. I don't have the photographs of the failure, but I have the photographs after it was repaired, the repair works, okay? Excessive deformation. This also along this road, as you see here, we see a lot of horizontal deformation of this wall, which is, of course, not good at all. We see that. Generalized failure. Okay, how to deal with generalized failure? In the beginning, when it started, of course, you didn't have a computer program, and doing slip stick was very, very hard. And that's why Professor Nunes developed this kind of, developed the math for this wedge failure. And the wedge methods has been used a lot until now. Of course, we don't do that anymore. We do a global stability analysis, It's very easy. And this that was the proposed by Professor Nunes and Dr. Veloso in 1963 Pan American Conference, this kind of wedge. And the German, a few years later, proposed something totally different with two edges, not totally different, but instead of using one wedge, the Germans used two wedges. These were the pioneer works in that area. The wedge method, now, it's very simple. We have this kind of equation that we can use. This I just pulled out from Herc's book. Very easy. But today we don't use this anymore. Today what we do is slope stability analysis. This from Hooker Bray, 1981 book. What we do now is a global stability analysis, and we calculate factor of safety. Okay, and I'm going to show you some examples. The other thing that we do today, in some cases, not all, but it's very easy now to do finite element analysis. This was the first Plaxi analysis I have done for a wall. And of course, now this program Plaxi is much more developed than it was at that time. This was 2000, I think. So 25 years ago. And today is very easy to do this kind of analysis and to analyze deformation and to compare the results with limit equilibrium analysis. So this is some results from this analysis. So, and this, the advantage of this, that you get the bending moments on the face, and this leads to the structural engineering calculation for the moment. And we have also the maximum axial force at every ground anchor or nail, okay? And here's some important and practical recommendations for distance between anchors when we do a design. Usually what we want is the grouted part, usually at a depth of 5 grout, the bonded length usually at a depth of 5 meters, and also minimum distance between nails should be 6 diameters or minimum 1 meter. What else is the minimum? Also, this distance usually is 0.15 of h being the height of the wall. Okay, so these are recommendations, and on plan view, what we do is minimum 1 meter or 8 times the diameter. The other solution that we have used a lot and works very well is when you have a soft ground that you may have the possibility of this to fall or to settle. We can support the wall weight by using these micropiles. These micropiles usually they are spaced 3 meters, 2 meters, and they support the weight of the wall. And now some examples, okay? This is a big wall being built in 1975, an immigrants highway that links São Paulo to the coast also. As you see, in those days, they used a lot of these multi-strand anchors without corrosion. And of course, we had lots of problems, especially close to the head where you have tension and flexion, okay? This was a milestone in this tour of this voyage. We have it was designed in 1984, Icaraí Beach, which close to Rio de Janeiro. It was a 35-meter high wall. It was a mixed wall, as a matter of fact. It has nails on the top and grouted anchors at the bottom. Today, we could design it completely different. Certainly, with everything could be only nails. Here's an example of generalized failure that I did many years ago in 1990. In those days, we didn't have very good programs to do fail analysis, but I had one in Fortran, and I did analyze that with the Fortran program. Oh, it was terrible in those days. And this was generalized failure, and the analysis have shown that the cause of failure, it was a very sandy material, silt sandy material with almost no cohesion. We had some tests done, site investigation done, and the analysis showed that the possibility of raising the water level during a storm, this was the main cause of failure. And I did this with a program that I wrote, not all the program, as a matter of fact, I used the stable program, which was written in Purdue University. I did some modification to include the fact of nails or grouted anchors. And this yellow line is a major corridor in Rio de Janeiro, and here these amphitheater for the port of the tunnels, two very large tunnels. They are 120 square meters in section. I did some work on the tunnels as well, but these help on the design of these earth retaining structures alongside the portal. And this is the yellow line. And here we had the solution here was grouted anchors, and the solution here was soil nailing. And this how it looked. And this at the same construction site, that's where we had a big failure during construction. And I did the analysis of this situation. It took place in 1995, and the failure was like that, you know. And this was the design. The design seemed to be very safe. Okay, it was an 8-meter high wall, and the soil is very hard. SPT values, any values between 28 and 40, no water. And these are the parameters that we have used. These are residual soils, okay? And we had lots of laboratory tests to confirm these values. And we had the design showed the factor of safety of 1.4. So everything seems to be very nice. The design was okay. The problem was the construction. Okay, they took it from the top, and they excavate after two anchor levels. They decided to excavate without excavating niches, as Professor Costa Nunes developed this methodology long ago. They decided to excavate everything at a time. It was a construction problem. Okay, and the factor of safety that they came up doing a back analysis of this was 0.9 because of excessive excavation. So this is the part that failed from here to here, and this was reconstructed after that. Okay, a new wall was put here. And this was a major challenge a design that I've done in Peru in 2011, so 14 years ago. And this is a crusher, a big crusher of this Toquepala mine. This is a very interesting site. It's about 3,000 meters of altitude above the sea level. Took me a couple of days almost 3 days to get there. And this is the South Peru, and very difficult to, there's a winding road to get there, but very, very, very interesting because it's a desert on the top of the mountain. And this is the new crusher that had to be designed, and this was the design. This compacted soil and these anchors, And I did the analysis, a lot of stability analysis, factor of safety without anchors 0.34, without anchors, no seismic value, 1.94, and anchors plus seismic value. I did pseudo seismic analysis, and in this area, the ground acceleration is about 0.3, so it's very, very high. And so we have to allow for seismic design as well. And the working load, there was a kind of discussion about what we should do or should not do. The working load is Tmax divided by a factor of reduction factor. Okay, in Brazil we use 1.75. In Hong Kong we use 2, but the Federal Highway Administration, the manual that I had access at the time, allowed 1.33, which I found too low. Okay, so there was a big discussion about that with the client, which was the mining was South of Peru Copper Corporation, and in the end we decided to use 1.75, which is the minimum that we felt comfortable. And also we did today we can do this easily. We did finite element analysis, okay, and to check for the deformation, and usually the deformation had to be my own criteria is to limit the deformation maximum to 1% of the wall height. In this case was 41 millimeters, so no problem at all. Okay, and moments this allowed to obtain moments for the circular design of the wall, and these some pictures of the wall being constructed. In this case, we were not very much concerned about the corrosion. And why? Because this is a very, very dry area. The average annual rainfall is about 3 millimeters only. So no corrosion problem, okay? And this, of course, won't last 20 years. This may last 10 years, more or less, this structure, until the mine is finished. So we didn't allow very much for corrosion because of this situation. And these some photographs of the excavation that took place, the initial construction, and the multi-strand anchors that we have used there. This is also in 2018 an old wall that failed due to corrosion. This is in Brazil, in the close to a city called city named Belo Horizonte, and this is the new wall, and we did a lot of analysis of this. So this is the angle corrosion that I have seen in the wood strands, and my guess was that this was the problem. He is one of the wood strands anchors corroded. And in this case, we did a lot of limit equilibrium analysis. Now we're using new programs, something that we can do today very easily. We have, this program was stable, stable 6 by rock science. And we did also Plaxis 2D finite element analysis to check the parameters, as I said, check the deformation. And here, as you see, we have a series of walls to be reconstructed, and these are the anchors. As you see here, this was the design by someone else. When we came to the construction site, this was the design, and what we found, too long, not necessary. So we able to advise the clients not to go through these too long anchors, and they could be reduced in length. Okay, the analysis showed this very, very easily. Also, he came up with moments and shear values in order to uh, design the walls, the concrete. And here's some examples in Hong Kong, where I worked for some time. Most of the walls I have seen in Hong Kong were soil nailing, made by soil nailing. But this in Pak Phulang Road in the island, this was perhaps the only one I've seen that they used ground anchors. And in Hong Kong, they didn't like to use ground anchors because they thought, "I know we have to to measure the loads alongside for a long time, etc., which is not the case." And so there's some pictures of this uh, structure in, and this one of the most complex works I have done in terms of walls. This took place last year in Gloria Hotel. Gloria Hotel is a very, very old structure, a very old hotel. It's about 150 years old. And in the basement, they have lots of these, I think, eight, if I'm not wrong, eight retaining walls. And some of them had to be completely modified. And this was one of the most complex I have done because we didn't have space. We and here there were the foundation of the walls. We couldn't have tiebacks here because the possibility of going through the foundation. So we have to we put this wall, it's about 6.5 meters high, and this wall with this very small base had to be anchored in order to pass, not to overturn. Okay, so this was one of the most complex because of the constraints, geometry constraints in the basement of an existing hotel, a very old hotel, which is protected. So, final remarks. I'd like to say excellent experience since the 50s, used as a rigid structure. Corrosion in unprotected wood strand anchors may be a problem. Today you have solution for that. Dividag, as I've shown you, they have very good solution. Something which is very important, I have talked about this in another class. Always, if you have the possibility of raising water level, you have to consider an RU value for rainfall. My experience to back analyze lots of failures, usually I take RU value or pressure value of 0.2 to 0.3 in areas where we may have severe rainfall. Of course, it's not the case of Peru, the Toquepala wall, because they have only 3. But areas where we can have severe rainfall, we have to take that into account. And today we can design with limited equilibrium method, which is very good, and also check the design with the finite element method and to check the factor of safety. I've shown you some recent analysis, and also we have to design for construction stages, not to make that error that I have shown you before. So these are the end. This is the end of this part, and I'm going to stop sharing here. And I'd like to make 1 minute to 2 minutes. Stop sharing. 2 minute stop, and I'll come. I have some. The slides. Bruce is talking about the slides. Link it in the chat. They're not the same. Well, there's an update. I'm going to send you this update. And so it's a question about only the slides. The other thing I'd like to recommend you is uh, most of what I talk here, not everything, of course, but comes in my book from my book on the Handbook of Stabilization, came up in uh, 2004. Okay, and it's free. You can get a copy of it. Either you ask the insight or you can send me an email. I'll be very pleased to send you a copy of this book. So let's have a 2 minute interval and then we come back. Okay? Just a second. Unmute. On okay. Uh, okay. Let's go ahead and talk about soil nailing. This is very interesting as well. So introduction about soil nailing. We're going to talk about the use, the origin, concept, comparison with tieback walls, and analysis. More or less the same type of analysis, limit equilibrium, finite element analysis. Applications. These soil walls have been applied to existing slopes or excavation. Can be up to vertical excavation, but most of my applications, they were existing slopes. Okay. And the construction phases are, first we excavate the bench, usually 1 meter, 1.5 meter deep bench. And then we store the nails, okay? And after that, we spray concrete. That's the most common application. And this is what exactly was being done at the Yellow Line many years ago, and in which they were excavating and putting the nails in. You know, usually in most cases, the nails have a spacing 1.1, let's say 1.5 to 2 meters spacing, and the length varies, of course, with the height of the slope and inclination. So soil reinforcement, we have reinforced earth, which you take from the bottom. It's use compacted material, and you put the reinforcement as you go up. Okay, geosynthetic reinforcement as well. Okay, but soil nailing, just the opposite. We take it from the top down. Okay. As we said before in the previous presentation, until, let's say, until 70 something, we only have the active reinforcement. My professor at school, Professor Nunes, used to talk about passive reinforcement, but as far as I know, he never applied. Most of his experience was with active reinforcement, the tieback walls. Okay, but he talked about that in school. I still remember that. Okay, and the passive reinforcement, as I said before, it has no pre-stressing, and how it mobilizes friction when there's a trend for this wedge to move. Okay, and not applicable to where a 1 meter high bench cannot be excavated. For instance, if you have soft clays, no way you can't use this technique. It must be stable for a minimum of 1 meter bench to be excavated to be stable. Okay, cannot be used in very soft clays. Uncemented coarse sand, beach sand, for instance, doesn't work because you're not going to be able to excavate 1 meter vertically. Okay. And what's the advantage? Economy, it usually costs about half, let's say 70% to a half of a tieback wall. Construction time is very fast as well. You can use any wall inclination, okay? Of course, you can do the same in tieback walls, but most tieback walls are vertical because that's the way it has developed. But we can use this with any wall inclination. Of course, not overhanging. Behavior is very good in many cases. And excessive displacement can also, it's a more flexible solution, okay? But these additional displays can be controlled if it's necessary. I'm going to show you that these techniques can be controlled with additional anchors to have a kind of mixed solution, okay? Milestones. As far as I know, the first of these walls have been being built in Versailles Chantier and analyzed. Okay, we have some experience in Brazil which took place in 1970. I'm going to show you, but without any analysis. And 1979, the Germans came up with the first analysis method, and then the Davis method came up in 1981, multi-criteria 1983, the French method, and 1991, the French carried out a major research project named Cloutaire, and this was a very important milestone to understand the how these kind of walls behave and how to design, etc., etc. Today, we don't use these methods anymore because we use computers and we use, limited equilibrium analysis, which I'm going to show you later on. How do we install the nails? We carry out a borehole with a hydraulic rig like that. So we can use a large one. This one, for instance, is air-powered, with air pressure, okay? Can be hydraulic as well. And we carry out a borehole, and then this is a pneumatic drill rig. And also, if you are drilling in a slope, you may need a very light hydraulic drill rig, and this is one of them. This piece stays on the ground, and this goes up on the scaffold, okay? And nail head details. These are nail head details, this case with two meshes, steel bar, and shotcrete, okay? Or it can be very simple. Sometimes with one steel mesh, the nail is bent like that, and we have a shotcrete layer, minimum of 50 millimeters. In Hong Kong, for instance, I remember they used a minimum of 75 millimeters. But this is for inclined slopes. You should not use something like that, the bent bar on a vertical slope. A vertical slope had to be something more elaborated like this with the plate and the nuts, okay? We can use also, as I've told you before, steel fibers instead of steel, sorry, I didn't tell you before. Steel fibers can be used in concrete instead of the steel mesh. There are lots of applications of that. I have used that as well. And recent trends for nail head details, okay? As we used a lot of these soil nails. In vertical facing, we always use the plate, okay? We can excavate a niche in order to avoid the protruding on the wall. We can excavate a niche and store the plate inside, and this is shotcrete. But if you have an inclined facing, you can use this kind of some people call it the chicken foot, in which we just bend the bar and it works. Okay. Some examples. Let's go back. Let's go to France first, where they started doing lots of work like that, and they developed the analysis. They did the Cloutaire research project. So this is probably the first. It's a wall, sol cloué, which is the French term in Versailles. And as you see here, they have very short nails, not like 6 meters, and here 4 meters, so very short. And they did as they did in tunnels. And why? Because these techniques seem to have developed from tunneling. And they have the primary layer, shotcrete layer, and then a secondary layer of concrete. That's the idea, okay, at the time. Probably this comes from tunneling engineers. And also, this is a big one, 21 meters high in those days. And in order to control settlement, in order to control lateral movement, they used a mixed design with ground anchor here, pre-stressed ground anchor, and they use here what in French is connière battue, in which they are driven steel sections, L sections, and they had 8 meters length here, 6.5 meters here, and the total height was 21 meters. Okay, the difficulty was at that time to do the analysis. Today is easy. At that time, it was very hard. Hong Kong. I have worked in Hong Kong, so this is the island, and it was a fascinating time in my career. This is my Chinese name, which I'm very proud of. Everyone has to have a Chinese name. My name is On Pato. To write the on is quite easy. To write the pa is easy. The to, it's impossible for me to write. I never learned how to write the to, so I have printed copies of it. Anyway, while I was in Hong Kong, I approached the Geotechnical Engineering Office, the GEO of Hong Kong, and I had the possibility of visiting a few sites to learn from them. And this is one of the projects I visited, Castle Peak Road. This is in on the island, Hong Kong Island, and I visited the site. As you see here, very interesting. They have this part of the scaffolding is steel, but most of it is made of bamboo. For the first time in my life, I saw lots of bamboo being used for scaffolding. That's the normal technique in South China. And as you see here, the bamboo allow people to go up on the hill to store the nails and then to apply the shotcrete. This is nail installation with that kind of light drill rig. This is a pneumatic machine which operated from here, and the air compressor is down at the bottom of the slope. And here they could easily store, as you see, the scaffolding made of bamboo for the first time. Also, these are pneumatic, very, very light pneumatic rig, the same another site I don't remember anymore, but here's the rig, and we used something very, very similar to make the road. So this Castle Peak Road, and this technique that I learned there, they always put the head nails in niches, okay, to avoid the protruding aspect of the protection cap. And this, while I was in Hong Kong, I had some work to do in Malaysia, and I visited Malaysia a couple of times, and I had the opportunity of visiting this site, in which very different at the time, in which they had a vegetated facing, okay, no shotcrete, and this is a green solution which later on we are applying in many projects that I have done, especially those in which we have a correct inclination of the facing to do that. It's nearly impossible to do, absolutely impossible to do it vertically. But when you have an inclined slope like that, it's possible to have a much environmentally friendly solution. And Canada, I have worked in Canada as well, 1990, the end of 91. And also I visited lots of projects, interesting projects in Vancouver. And this was one of the major drill rig I've ever seen, an enormous drill rig. It's in the city center in Vancouver. And this is an excavation for a building. Very interesting. This area here, they could put the nails in, but this area, they could not, for the neighbor would not allow them to put the nails in, so they had to use props like that. Also, these are temporary shoring, that soil nailing vertical wall. But Vancouver soil is very, very hard. It's something like SPTs should be something like 100. So they have a very good soil to do soil nailing. No problem at all in terms of strength. I have done some work in Argentina as well, And this is a project that failed before I visited the site, and due to excavation, etc. And this is a soil nailing wall, and it failed during construction, and I came up with this solution with filling with stuff with bags and then shotcreting it again, no problem. And some examples in Brazil, of course. And the Brazilian experience I've told you before, we started in 1957 with tied back walls, and then we developed to 1970. There was the first soil nailing wall in a tunnel portal, okay, in São Paulo. But this was done, like the French, by tunnelage engineers without any calculation. They, in those days, these tunnelage engineers used to put boats, to reinforce the tunnel, and they decided to do the same at the port. And that was the first Brazilian experience in 1970 without any calculation. Calculation came up much later. 1984, they didn't have a method for that. That was when mainly the French were developing the calculation method that came later. And I started working on that in analysis optimization in 1989, when programs became available, etc. And I did some work on this. And this is the first application in 1970. It was a tunnel in São Paulo, in which the port was protected by these nails. At the time they used to call it the boats. They didn't have this word. And then after that project, people started to use this in a few applications. Some of the applications that I know of the time. Excavation, inclined slopes, because there was no way of doing a vertical wall. This is it's a project in the north that worked very well with shotcrete, and this a bridge abutment. It was reinforced. These phyllites, and this has been reinforced by soil nailing. And this was the major wall. It's a mixed wall, soil anchors and nails. Without proper analysis, they could not be done in those days. Now we can in nice saprolites. And this kind of wall behind some high-rise buildings in Niterói. This is another project in which they decide to nail underneath the foundation of this one-story building. Permanent shoring, vertical shoring here. I don't remember where it was. And then this was one of my first projects, which I did the analysis for a contractor. And in my first experience in 1990 with proper design. In those days, in Rio, they had the Rio that belonged to the city hall. And Rio, they were very much influenced by tiebacks. They only used tiebacks. And that's when we decided to do some experiments we proposed them to do the experimental wall. And in the beginning, they were very reticent. They didn't want to use soil nailing. They thought, no, it won't work, etc., etc. Okay, and then I approached them. The president of GRE was a very wise man at the time, and I told, why don't we do some tests? And he said, okay, I'll pay you to do some tests. And this is it was the first experimental wall that we carried out in 1992 with shotcrete, and we did a lot of research. It was not a very high wall. It was about 4 or 5 meters. I don't remember exactly, but we installed some strain gauged nails in order to measure the distribution of loads along the nail. And it was not a very high, and it was in the end. There was a tieback wall, and then they allowed us to do the experiment along a 30-meter long wall. Okay, and the experiment went so well that they decided to go ahead. Then the another university, the Pontifical Catholic University, did also a trial wall in 1994, and it was they developed here a few thesis. It was a doctoral thesis from a friend of mine, this experimental wall. And after this, Jerry decided to buy the idea, and today they do a lot. Okay. And there was another development that took place later on, but these friends of mine from the company called J.O. Green, they decided to do something very similar of what I've seen in Malaysia. As a matter of fact, they came to me and I told, oh, I've seen this, etc., etc. This works. I've seen this wall in Malaysia. Why not? Why not to try? But then they had invited a forestry engineer to work with them to come up with the vegetation solution. And this one of the very successful experiments. It was a big slope, about 10 meters high, and then they used these nails. They are 1.5 meters spaced. Some of them are longer. I don't remember the details. Was not directly involved here, but what they did was it was a 65 degrees slope, and they vegetated this slope, and also they this was the most difficult part, in which the nails have been installed, and then they are doing these small holes in which it was recommended by a forestry engineer in order to the seeds to stay there and to be able to grow for the to have a vegetated facing. Okay, so that's the way they worked. And later on, when the nails are there, these small surface holes were made. They put up a biomesh and they select the seeds, the type of vegetables that would grow in that particular site. And a few months, that's what we see. It's a very user-friendly solution and not expensive, perhaps less expensive than the uh, the shotcrete, and much more beautiful. And this is something that we are using a lot today. And also the American experience, most of American experience is in this manner, which is very good. I recommend you to have a look. It's free, of course. You can download from the Federal Highway Administration site, and I propose that you have a look at this. Let's talk a little bit about design, how we do the design. Design stages are site investigation, of course, very important. Something that I recommend is, even if you don't have a groundwater, in areas where you have rainstorms, like those I have been working in Brazil, in Guyana, in Venezuela, we always have to take into account the possibility of a rainstorm to increase the groundwater pressure and to raise the water level. I've seen this too many times. And usually most of the back analysis I have done in slopes that failed leads to an RU per pressure value of 0.2, 0.3. Okay. You have to do pull-out tests in order to be able to design the nails. The problem is I never did pull-out tests before. I never, no, except in Brasilia. Brasilia, for the, I managed to come up with some pull-out tests before the actual construction. But in most cases, in 99% of my cases, I was not able to do pull-out tests before the construction. I have to assume some friction from, usually I use that correlation between SPT and friction. And later on, I check that during the initial, when they start construction, the initial phase of construction. Then we do a stability analysis, and today we can do also deformation analysis when it's needed. In most cases, not needed. Sometimes, but it's easy to do today. Okay. Site investigation, we do is a trigger-free, groundwater, strength parameters, soil nail friction. Pull-out test before construction. A major project, this is something that you can do in order to test different materials if you are going to put nails in different soils or rocks, okay? And so nail pull-out test, this is a typical arrangement to carry out this kind of test. Very simple, as I've told you before. This French experience in which they came up with a jack held by this hydraulic rig in order to make many tests very fast. They could move it alongside the work, many tests, to do several tests, a jack and a load cell. And this is my suggestion for coming up with a QS value, which is the friction. Okay, you have here very good correlation. In many soils, we have silts, sands, porous clays, silt, everything related to the NESPT value, because in most cases, that's what we have. So I can come up with here and have an idea of, for instance, if I have a soil with a SPT of 10, I will come up here, I can assume something like 100 kPa in most cases. If you have a much better soil, you can double that value. And this has been published in 1997 by Professor Palmeira and myself. If you have multi-stage grouting, okay, this may be advantage or not. If you have two phases, you can take at least 50% increase in the QS value, in the friction value. Method of analysis. We have a lot, okay, but these methods have been developed before the computers are very good. So the first one was German by Stoker, Davis, multi-criteria by Schlosser, French engineer, French professor, kinematic by Giron, also a French professor, Cardiff method by Bridle in 1989, yield method, and I developed my own, which was very simple. I used the stable program, which was developed originally by Purdue University, and I just included the effect of the nail in tension, okay? But in those days, programs are very, very crude. They didn't work very well. So that's why I had to develop my own program in those days. Now I don't use that anymore. And the German method, the initial German method was with two wedges, like very, very similar to what they use for the tieback walls. And Davis, they used a parabolic failure surface. Cardiff, they use a log spiral, and small difference. And multi-criteria came in 1983, was very good because was the first to take into account the shear. Sometimes it's important, not all times. And how the nail works? It's here. You have the active zone. Here you have the nail, and the QS is working in this part here. And how do you take into account the tension, which is the most important thing on the nail? Is a very simple equation in which here you have the perimeter times the friction times the length, okay? And also the multi-criteria, which was the first to use the bending or the shear, they have some equations to calculate that. And this was later on incorporated in a program which I'm going to show you later on. Tensile and shear reinforcement. in most cases, I would say 9% of the cases, only tensile on the nails is necessary, okay? Unless you have nails which has a bending stiffness, like mini palms, okay? Then shear could be more important. I have done some research on that, and this is a comparison between the method that have been developed in 19. I adapted this from Gigon de Mine in 1986, and here what I have done, and I published this result, but today is completely out of date. I'll show you what we should use. In 1997, I used this Talham program, the French program. It was very good, but now it's out of date. And today, most programs like Plaxis, Rock Science, or GeoStudio, most of these programs they have reinforcement. So what we should do is to use one of these very easy programs to learn to use, and they have reinforcement for this. An example of one of these finite element limit equilibrium program in which I did slide analysis. This is slide 6, and then I put the reinforcement in, and I did how to put the reinforcement. We can here we calculate the bond strength from the friction. You calculate this, you calculate the tensile capacity, plate capacity out of spacing. Usually the spacing we tend to use is 1.5 meters. And then the program easily calculates the factor of safety for you. And that's the kind of design that we do. I have done a lot of work on that R-stable program, but this is totally out of date today. And today you can do also a deformation analysis. In the past, it was very difficult to do that. And today is easy. In most cases, if you have a maximum deformation up to 1.5% of the height, it's more than enough. And here, it's a quiz for you, which I'm not going to tell you the answer today. I leave for you. Anyone want to discuss this later on can email me or text me through WhatsApp. And the question I would like to ask you: what in these three cases? All these three cases they have the same factor of safety of 1.5 on the limit equilibrium. But if you do a deformation analysis, which one do you think is going to have the least deformation? Okay, I'm not going to tell you now, but you're welcome to discuss with me that later on. Design for deformation. Sometimes you have a situation like this, which of course I have faced before. You have a shallow foundation or deep foundation close to a wall, or you have like the Tokepala wall, which I have to design for very, very big lorries, out of road lorries, and I have to consider that in the design because I have to consider the deformation. So here we can have, for instance, you have to what you can have here is a a special design in which here you have to put more nails, more anchors in order to limit the deformation, and this is not applicable to the sides. So usually soil nailing, the maximum deformation takes place on the top, and on the other hand, reinforced the earth due to the construction method from bottom to the top, the maximum deformation takes place like this. And your horizontal displacement today is very easy to do a finite element analysis like this one. And you can come up with a solution like that. For instance, a tied back wall here and a soil nail wall on the other part in order to prevent large deformation very close to the foundation. And this is a kind of mixed wall in which we can have soil anchors and naves, and these can be analyzed through finite element. The other thing which is very, very important, you have to take that into account, is drainage. And here, what kind of drainage that you can have. You may have whip holes, we may have a geosynthetic for the face drainage, you can have a channel here, you may have a deep drain. Deep drains are not a permanent solution. In most cases, they clog with time. So I always design deep drains as a temporary solution. Okay, and here you can have French drains in order to get the water up here. And this is a better drawing of these sub-horizontal drains with holes, 2 layers of nylon mesh, and this put here in order to catch the water. This is a temporary solution. They do, most of them do clog with 5 years, 6 years, or even less. Okay. Face stripe drains, I've used these in the past in order to avoid whip holes, because whip holes sometimes it's not very nice. So I have used these in the past, and these drains lead to a pipe, collector pipe in the back. And finally, instrumentation. This kind of research instrumentation I have done in the past with surface marks, piezometer, strain gauge, and inclinometers. Inclinometers are very important in high walls. During construction, it's very good to have an inclinometer for you to measure deformation during construction. Today, we would replace most of these instruments by IoT devices. I mean, automatic devices. This is easy to do. Today, we can automate the inclinometer with the shape array. Piezometer can be automated, etc. So major project, a small. You're not going to instrument a small project, but large, very large project, very high. You may be interested in doing the instrumentation. I have another lecture on instrumentation, which I'm not going to cover today. And as concluding this presentation, we've seen soil nailing can be applied to slopes and excavations, used since 1970. That's the first. Economy in relation to tieback walls is about half of the cost. Proven design methods for stability, for deformation, and it's not difficult to do that. So that's the end, and I'd like to acknowledge the support I had from my friends from Geo Green, my friends from ZR, they are contractors, and my friends from DVDAG, who gave me some information. Here at the end, you have my email, you have my WhatsApp number. You can talk to me text me at any time, and I look forward to receiving information or results from that quiz I've sent you about the deformation of the wall. And okay, I'll stop share, and may I have a look at if there is. Okay, there's a question here by Bill Friedman. Thank you, Bill, for your question. May I read it? Most of all your examples are walls upslope of road cuts, except the formation towards the end, of course. What the preferred method, in your opinion, when try to stabilize a hillside below road cut and you have a traffic surcharge load to consider? In particular, when there is a slide below road on the steep slope and the type of excavation you propose is impractical. In California, Caltrans tend to use poly-based design for these conditions. Okay, well, it's possible to use poly-based design. Of course it is, but it's very expensive. You know, I never stabilize a slope with piles. It's very, very expensive. It's much more efficient to use tensile stress rather than bending stresses. Okay, bending it would cost much more. If you have, for instance, if you have a hillside below the road, if you had already a failure, that's more complex. If you had a failure, perhaps on the top you could use a tieback wall in which you it's possible to do a tieback wall in which you compacted the soil as you build as you build. So if you put a wall, you can like the Tokepala one. The Tokepala, the material behind the wall is compacted. As we the difference that wall, although it was a tieback wall, it was constructed from the bottom up. Okay, you can use that and compact. Also, you can do a mixed solution. If you have a cut, you're going to bring a wall to the top, and then you can excavate from the bottom. I'd like to discuss this with you. If you send me kind of drawing, or if you want any information, I'll be available to discuss this with you. But in most cases, I would say that piling is not efficient as tensile stress on the nails. Okay, so that's it. If you have any, if you don't, I don't see any more questions. So I thank you very much, but I'm available for any additional discussion you may have. Okay? Thank you very much.
Yes, we will have the latest slides today once I coordinate with the professor, and will be posted sometime today. And the quiz will be available probably tomorrow morning to make sure it's the same as the slides. So allow us a couple of hours to coordinate. Thank you.
Okay, thank you very much. Yes, I'm going to send you the slides right away. Okay? Thank you very much. Bye-bye.